In our first video in this section on epistemically loaded uses of the term law, I ended that video with this claim that all the interesting issues related to the use of the term law are tied up with the epistemically neutral meanings of the terms, meanings that don't presuppose anything about the degree of evidential support that a claim has. Here's a reminder of the sample of laws that we looked at. We had a selection from biology, a selection from psychology, and a selection from physics and astronomy. Now, what's one thing that all these law statements have in common? Well, here's probably the most basic feature they have in common. They all express generalizations. They make a claim about a whole class or category of things. They don't refer to particular individuals or particular objects within a class or a category. They say of a whole class of things that such and such is true of this class. In logical terms, you would say that law statements express claims that can be written in the form all A or B, or no A or B, where A and B represent classes or categories, all bodies with mass, all planets, all organisms, all mammals, and so on. Sometimes the law is actually written in this form, but there are lots of grammatical constructions that are logically equivalent to a generalization like this, and this is the case with the examples that we've seen. If you're curious about the no A or B form, an example of a law that's commonly written in this negative form is the thermodynamic law that says that no perpetual motion machines exist. Or in relativity theory, we often say no body can travel faster than the speed of light. So those are just examples. So this is one feature that all these law statements have in common. They all express generalizations. Here's another feature that law statements share. Law statements allow us to make counterfactual inferences. This is just a fancy way of saying that they allow us to make claims about what would happen if the facts were different. So, for example, if I walk to the edge of a ledge and keep on walking, Newton's laws predict that I'll fall, and I'll fall with a certain trajectory. But that prediction holds even if I don't actually walk off the ledge. Let's say I stop walking. It's still true to say that if I was to keep on walking, I would fall off that ledge, and I would fall in a certain way. Now, why is this true? It's true because it's entailed by the laws of physics. That's an example of a counterfactual inference. In the actual world, I don't walk off the ledge. But the laws of physics let us investigate what would happen if I did keep on walking. Let's take an example from biology. Similarly, Allen's rule or Allen's law, which we saw, says that animals that live in warm climates have longer appendages and more surface area per unit of mass to help radiate heat. And animals that live in cold climates have shorter appendages and less surface area per unit of body mass to help conserve heat. This desert fox has big ears, as you would expect according to this law. Now, let's assume that you didn't know whether there is an Arctic version of this fox. If Allen's law is right, then we could predict that if there was such a fox, it would look different from a desert fox. We could predict that it might look something like this. Smaller ears, shorter legs, rounder body. Now, this is a real Arctic fox, but the point is that even if there was no such fox, Allen's law, if it's valid, would allow us to say something about the features of such an animal if one did exist and lived in the Arctic. So this is a second feature that law statements have. They play a special role in our reasoning about the natural world. Laws of nature allow us to describe not just the way the world is, but also the way the world would be if the facts were different. In philosophy of science jargon, we say that laws support counterfactual inferences. Not all generalizations have this feature. Just to give a simple example, here's a generalization. All the people who will ever live on this block are under 7 feet tall. It's a universal generalization, it has the right form, and it's very likely true. Let's assume it is true. So it's a true universal generalization. But it would be very odd to say that this expresses a law of nature. If it's true, it's only accidentally true. There's nothing preventing a 7-foot tall person from moving to this block. So one way that you can distinguish these kinds of accidentally true generalizations from genuine laws is that they don't support counterfactual inferences. They don't tell you anything about how the world would be different if the facts were different. And this ties into the next point. Here's a third feature that law statements have. They seem to play an important role in our metaphysical understanding of the structure of the world, and in particular, whether an event or a class of events is physically necessary, physically possible, or physically impossible. Let's go back to our guy walking off a ledge. I walk off that ledge. What will happen? Assuming we're on the surface of the earth, I'll fall. Why will I fall? Because the laws of physics necessitate it. It's not physically possible for me to just walk off that ledge with no support and no other hidden forces acting on me and not fall. Given the laws of physics, I must fall. This notion of physical necessity is an important part of our common sense understanding of the world. The fundamental laws of physics, in particular, play a key role in defining the boundaries of what is and isn't physically possible in our universe. The broadest concept of possibility that we have is the notion of logical possibility. This depicts the space of logically possible events. To qualify to get into this space, you only need to avoid logical contradictions. The world can't contain genuine literal contradictions, where a statement P and its logical contradictory, not P, are both true at the same time. Then, inside this space of logically possible events, you have the space of physically possible events. These are events that are consistent with, that don't contradict, the fundamental laws of physics, or as some would say, the laws of nature. The laws are what define this boundary between what's physically possible and physically not possible. Then further in, we have another subset, the space of physically necessary events. This is what has to be true given the laws of nature. So the actual world that we live in is going to occupy this space. If an event is physically necessary, then by definition, it'll be part of the actual world. But lots of things happen in the actual world that don't have to happen. These are events that are only contingently true, meaning they could have been otherwise. They're not necessarily true. Anything that happens must be physically possible, but it doesn't have to be physically necessary. So events in this dark blue region are physically possible events that in fact occurred, but didn't have to occur. The number of planets in our solar system, for example, isn't necessitated by the laws of physics. It's a contingent fact of our particular solar system that it has the number of planets it does. Similarly, the evolution of human beings is consistent with the laws of physics and the laws of biology, but no scientist believes that the evolution of Homo sapiens is a necessary consequence of those laws. Now, the reason why I'm sketching this picture is to make a point about the role of laws in our understanding of the world. Historically, one of the ways people have used the concept of a law of nature is to express our shifting understanding of physical necessity or biological necessity, or even psychological necessity. To talk about laws of physics or laws of biology or laws of psychology is to talk about what is possible, what is impossible, and what is necessary within these domains. That is one of the roles that the concept of law has played in our scientific vocabulary. So I think I've made good on this claim that all the really interesting issues concerning the concept of a scientific law are tied up with the epistemically neutral meanings of the term. Here we've looked at three distinct roles that the concept of a law plays in our scientific understanding of the world. First, and most obviously, laws express generalizations about the world. They make claims about entire classes or categories of things. They capture patterns and regularities in the phenomena and in relationships between physical properties. Second, law statements make claims not only about what happens in the actual world, they also tell us about what would happen if things were different from the way they are. We say that law statements support counterfactual inferences. We use counterfactual reasoning all the time in science. And third, law statements tell us what events are physically necessary, physically possible, and physically impossible. These distinctions are part of our common sense understanding of the world. The laws of nature express our current understanding of how to draw these distinctions. And finally, just a reminder, all of these ways of talking about laws are epistemically neutral.